Does the distance between x and y equal the absolute value of x minus y over 1 plus absolute value of x minus y? Define a metric on R. To check if it does, we need to verify that it satisfies the following metric space axioms for all x, y, and z being real numbers. The first one is non-negativity. We want the distance between x and y to be greater than or equal to 0, and the distance of x and y equals 0 if and only if x is equal to y. So starting with that, we know that the absolute value is always going to be non-negative. So when you divide non-negative numbers and you add a non-negative number, you should get a non-negative number. And we know that if the absolute value of x minus y over 1 plus absolute value of x minus y equals 0, we can multiply both sides by the denominator and get the absolute value of x minus y equals 0, and that means that x has to equal y. Next, we want to show the symmetry is satisfied. So the distance between x and y is equal to the absolute value of x minus y over 1 plus absolute value of x minus y. And we can also change the order of x and y. So instead of subtracting y from x, we do x from y. And we know that's still going to be the same. So the distance between y and x is the same. So what's left is the triangle inequality. Let's define a new function. We'll call it distance of x and y, or d prime of x, y, equals the distance of x and y over 1 plus the distance of x and y. We aim to prove that the distance between x and z is less than or equal to the distance between x and y plus the distance between y and z. Okay, so first note, the triangle inequality tells us this is true. So we're going to define A to be the distance between x and y, B to be the distance between y and z, and then C to be the distance between x and z. From this, we have that if we substitute it back, C is less than or equal to A plus B. Now let's consider the function f of t equals t over 1 plus t. And this is for t being greater than or equal to 0. The function has two important properties. The first one being f is increasing between 0 and infinity. And that's because the derivative is 1 over 1 plus t quantity squared. And that's always going to be positive for t greater than or equal to 0. And then the other property is that f is subadditive for all a and b greater than or equal to 0, meaning that f of a plus b is less than or equal to f of a plus f of b. And so we're going to prove this properly right now. So f of a plus f of b is a plus b over 1 plus a plus b. F of a is a over 1 plus a. And f of b is b over 1 plus b. So we'll multiply both sides by the denominator. Now we can multiply this out. We have a plus b times a plus b plus ab is less than or equal to, and then we can factor out a 1 plus a plus b to get a times 1 plus b times 1 plus a. So we have a plus b times a plus b plus ab less than or equal to 1 plus a plus b. and then times a plus b plus 2ab. And so we'll just look at each factor individually. 1 plus a plus b is greater than or equal to a plus b. And then a plus b plus ab is less than or equal to a plus b plus 2ab. Because when you cancel this out, you have ab is less than or equal to 2ab, and then you get 1 is less than or equal to 2. So then this inequality holds, so therefore this is true. So now we have d prime of xz is equal to d of xz over 1 plus d of xz, and that's going to be less than or equal to a plus b over 1 plus a plus b, which is less than or equal to a over 1 plus a plus b over 1 plus b, which is d prime of xy plus d prime of yz. And that's the triangle inequality that we wanted to prove, which means that the distance of xy equals the absolute value of x minus y over 1 plus absolute value x minus y defines a metric on R.